Okay, here's another picture, but now I've labeled this vector to represent 90 newtons in this direction, and this vector, the little white vector here, to represent 60 meters, and that'd be 60 meters in this direction. Now, make the statement, the projection of the force, this is the projection, well, okay, the orange vector here is the projection of the force vector, because 90 newtons would, we think, represent a force vector, 90 newtons being a force. The projection of the force vector onto the displacement vector, 60 meters being a displacement vector. Well, the 60 meters in this direction being a displacement vector. So that projection is represented by this orange arrow, and appears to have, to my eye, and you can have your own opinion, you can modify it, you're as likely to be right as I am, but my opinion is it's around 40% the length of this vector. This projection vector is around 40% the length of the vector that we projected. Okay? So, the projected vector, the 90 Newton vector, represents a force of 90 newtons in the direction of the vector. So the projection represents a force because, well, it's going to represent a force that's 40% of 90 newtons, or 36 newtons. So now we can say, okay, this projected vector, the projection, I'm going to write a statement here. I'll do it off camera. Okay, we say that the projection vector in this case is the component of the force vector in the direction of the displacement vector. Displacement vector is this direction. The component of the projection vector we estimate to be 36 newtons, the component in the direction of the displacement. And that component is the part of the 90 Newton force that acts in the direction of the 60 meter displacement. We don't need to use it right now, and you're not actually required to know it, but it's worth storing away because having done the projection, we get this vector here. Now this vector could be drawn from the point where the projection line meets the line of the displacement vector up to the tip of the force vector. I've drawn it offset a little bit, just as I've drawn the projection vector offset a little bit, and that doesn't hurt anything. The vectors are the same no matter where you move them. You can't change their length, you can't change their direction, but you can move them around. Don't worry about that right now, but that's one of the rules. Okay. That is the component. Okay. So these two vectors could be joined to make the sides of a right triangle with the force vector as the hypotenuse. And it's worth kind of noting that at this point. You're not going to be asked to do anything with that right now, but that's the case. And we'll look a little more deeply into this later. So that we've broken the 90 Newton force into a component parallel to our displacement and a component perpendicular to our displacement. If this is the displacement of some object that's being acted on by this force, and if this happens to be the net force, then this component is going to speed the object up. This component is not going to speed the object up, it's going to change its direction. So if I'm trying to move this way, and I've got a force in this direction, it's going to change my direction. Again, you don't have to know that, but it's kind of worth storing away. Okay, now the main thing is we need to know how to construct this projection vector, and there's one more thing then that we do with the projection vector. We won't mention this perpendicular component anymore today or even this week. The last thing you're going to be asked to do, or one of the last things you're going to be asked to do, is find the dot product of the force vector with the displacement vector. And that's easy to do once you have the projection and everything that we have here. You just multiply the projection of the force vector by the displacement vector. Now, I haven't stated that quite with mathematical precision. We multiply the magnitude of the projection vector by the magnitude of the displacement vector, and I'm going to insert those words. But the idea is simple. Our projection vector has magnitude 36 newtons. Our displacement vector has magnitude 60 meters. So we multiply 36 newtons by 60 meters. Now, in some cases, the displacement vector and the projection vector could be in opposite directions. If this 90 newtons was back over in this direction, then the projection would be back this way in the direction opposite the displacement, and then we would take the negative of that product. In this case, they're in the same direction, so the product is positive.